in the Q&A session. You can send questions anytime during the event. Also, this webinar will be recorded and posted online. As a start, I'd like to introduce to you the editors of the book, Professor Matthew Malkin and Professor Ben Zuckerman. They will be our moderators for today's session. Professor Malkin is a professor at the Department of Physics and Astronomy at UCLA, where he studies the evolution of galaxies and supermassive black holes using a wide range of telescopes. He's been active in scientific outreach programs since the 1990s and has worked extensively on astronomy-related films and television shows, both behind and in front of the camera. Professor Zuckerman is also from UCLA. Apart from his scientific interest on the birth and death of stars and planets, he has maintained a continuing interest in the origin of life, especially intelligent life, in the universe, and beginning way back in the mid-1970s, developed and regularly taught a course on life in the universe. He has co-edited 6 books, including Extraterrestrials, Where Are They?, and Human Population and the Environmental Crisis. And now I would like to hand it over to Professor Malkin and Professor Zuckerman.
Thank you very much, Brianna. We are so happy to have all of you here today for our conversation on the origin and evolution of the universe. A brief history of how we got here. That's an audaciously ambitious subject, but you don't have to worry. We have today possibly the finest panel of leading astronomers ever assembled that I know of to lead this discussion. And this is not an accident, because 6 of our astronomer authors came to UCLA in 1995 to do a symposium on this same subject and then published their contributions. Now, that was 25 years ago. What's changed? The answer is just about everything. First of all, the people who were already leading authorities at the time are now world-renowned experts. They've become even more famous with the passage of the time, and they're also selected for their brilliant abilities to explain their research discoveries to a wider public audience. But the subject itself has just absolutely exploded with discoveries from cosmology, black holes, exoplanets. We are in a second golden age of discovery here. And so it was high time to update the book with a second edition, which we've just published very subtly behind me. I have displayed here my 8-foot copy of the book. That's the large print version that I have. And this has 6 chapters from 6 absolute expert authors that we're going to hear from in order. And we also are delighted to have really the real moderator of this show, our super moderator, commentator, is Sir Martin Rees. Now, before I dive in, I'm just going to remind you once again, we want to hear questions. We want to have lots of time for the lively interchange that's stimulated by your questions. So you must go to the chat window, if you're familiar with that. It says chat on Zoom, and then pull the little blue menu down to find Ben Zuckerman. We want you to send the questions to Ben Zuckerman, the co-host there, and then he will read the questions to our distinguished panels, and then we'll get the conversation rolling. So we, once again, are asking you to keep your microphones and cameras off just to preserve our bandwidth for this very large webinar. Now, as I said, our super moderator and discussant, Sir Martin Rees, is a professor of astrophysics at the University of Cambridge, and he's worked on many areas from cosmology and what we call extreme astrophysics. He also has an interest recently in exoplanets and the search for extraterrestrial intelligence. And he's the astronomer royal. Enough said. I'm going to, in these introductions, by the way, I'm going to skip all of the prizes and honors and awards and elected fellowships and memberships for research and teaching and writing that every single one of these authors has received, because we don't want to embarrass them, and it would take the entire time we've got. But our first discussant from chapter 1, where do you want to start? I guess the most appropriate place would be the Big Bang, where we have a world's leading expert, Dr. Edward Wright, who is a professor of physics and astronomy here at UCLA. And in addition to his expertise on this subject, he played a leading role, in many cases, the leading role in 4 of NASA's most outrageously successful space observatory missions at long wavelengths. So my question to each of the panelists, starting with Dr. Wright, is what do you think are some of the most exciting advances and changes that have happened in updating the book to its 2nd edition? And perhaps where do you see things going further in the next 5 years or so to come? So let's hear from Professor Wright.
Okay, so in 1995, since 1995, the status of observational cosmology has really mushroomed. The 2 biggest things I would point out are the observations of the acoustic oscillations that come about from the Big Bang in 2 different ways, and the observations of supernovae later. But let's talk about the acoustic oscillations. Before the universe became neutral about 400,000 years after the Big Bang, the photon gas and the regular matter could support sound waves. And the speed of sound was almost the speed of light, a little bit less. And we can now see those in 2 different ways. We can see these as special spots on the sky, special characteristic spot size on the sky. And we can also see it in the distribution of galaxies. And so in 2001, as a follow-up to the COBE mission, the Wilkinson Microwave Anisotropy Probe was launched by NASA. And this mission mapped the whole sky with much better angular resolution, much higher resolution than the COBE mission. And you can see a fairly characteristic spot size on this little beach ball that we made from our data. And so that's one of the observations. The other thing that we see is currently, if you look at the distribution of galaxies, there's an enhanced probability of having galaxies about 500 million light years apart compared to 450 million light years or 550 million light years. And so both of these are due to the acoustic oscillations. So each of these observations then give us essentially a line through a graph of how much matter there is in the universe and how much dark energy there is in the universe. And by having these 2 observations, we can figure out the energy content, the dark energy content, and the matter content. And then we also get a 3rd observation, a 3rd line through this plot from the supernova observations. And these show that the more distant supernovae are fainter than we expect. Obviously, they're fainter because they're more distant. But in addition, they're fainter than we expected them to be faint. And that's due to the accelerating expansion of the universe. And that was picked up starting in 1998. So we have the supernova observations. We have WMAP launched in 2001. And then we've also had the Planck mission from Europe launched in 2009, and it made an even higher resolution map of the sky. So repeating the observations made by COBE and WMAP. And the galaxy surveys have really taken off. I mean, the galaxy surveys that first showed the acoustic oscillation started with the Sloan Digital Sky Survey. And now there are future plans with the Vera Rubin Observatory, which is under construction in Chile. And that will give us a very detailed map of the galaxy distribution. And also the Nancy Grace Roman Telescope, which was a space mission that will be launched late in this decade. And with both of those, we'll get much improved observations of the galaxy distribution and supernovae. So I would say that there's been a real revolution in observational cosmology already, and there's going to be dramatic further progress in the next few years. Thank you.
Thank you, Professor Wright. Martin, do you have any comment or response?
Yes, I'd just like to say that I think this is a really great story. The fact that we have evidence of what the universe was like when it was 50,000 times younger than now. And we can calculate forward from that and understand how those fluctuations evolve into a universe like the one we see. And so we can understand 99.95% of cosmic history. And I think this is a great story in astronomy, but I'd go further than that. I'd say it's one of the big advances in science, really up there with the standard model of particle physics and the genome project, to actually understand how from these initial fluctuations, which we see in the microwave background, we can understand the structure of the universe today. It's a great story.
Thank you very, very much, Martin. Well, so starting with the Big Bang, we now have the primitive primordial fluctuations that started to condense to make galaxies. And this is the subject of chapter 2 by Dr. Alan Dressler. He is an astronomer emeritus at the observatories at the Carnegie Institution. He's an expert in the formation and evolution of galaxies, and he observes them. He observes the process as it's happening with large telescopes. So, Alan, tell us about your chapter 2 and where the field is heading here.
Thank you, Matt. Well, my chapter is about galaxies, the giant star systems that are like lush islands in the emptiness of space we just heard about. From the perspective of life in the universe, galaxies are an essential step, believe it or not. We know much more about galaxies than in 1995, but very basic questions still puzzle us. We know that galaxies grow by converting hydrogen gas into generations of stars. But what regulates how fast a galaxy grows? Some galaxies turn all their gas into stars at a few billion years, while many, like our own Milky Way, are continuing to birth new stars even 13 billion years after the Big Bang today. My team has now found massive Milky Way-like galaxies whose growth started very late when the universe was already 6 billion years old. We don't know why star formation was delayed in such galaxies. A related but quite different question: how do the supermassive black holes in the centers of galaxies power quasars? By growing to phenomenal masses of millions or billions of times the mass of our sun. Recent data suggests that they grow more rapidly earlier in the universe than physics would predict. The modern study of galaxies began with Edwin Hubble and his 1918 observations with the Mount Wilson telescope that showed the Milky Way as just one of billions of galaxies, part of a universe that is really too vast for human senses. From then to now, a remarkable increase in our understanding of galaxies has come from detailed studies of individual stars grouped into stellar populations in our own Milky Way galaxy and in a few nearby galaxies. And just as importantly, through our unique ability to see back in cosmic time by looking far out into space, as Matt alluded to. As we met in 1995, we contemplated the great progress that had been made in understanding what goes on inside galaxies through ambitious and difficult research that relied on ever more powerful telescopes, increasingly sophisticated theory, and eventually modeling using ultra-fast computers. Today, in 2020, we are poised to make dramatic progress toward the unrealized goal of the 20th century astronomers to understand the physics underlying the complex growth of galaxies over 13 billion years. The huge cryogenic infrared space telescope, the James Webb, is scheduled for launch, is scheduled for launch 1 year from now and later in the decade, but already under construction. Will be a replacement for the Hubble Space Telescope with a field about 100 times wider and a new generation of truly giant optical telescopes here on Earth. With such powerful facilities, we will be able to perform galaxy archaeology on not just a few neighbors of the Milky Way, but more than 100 nearby galaxies. And for the first time, we will gather images and spectra of galaxies in the very epoch of their birth in the first billion years of cosmic history. It promises to be the most productive and exciting time in the history of the field we call galaxy evolution.
Thank you,
Matt.
very much, beautifully stated. Martin, is that?
Okay. First thing is we've learned a lot because we can do computer simulations. We can't really crash galaxies together, but in the virtual world of our computer, we see how they evolve. So we've learned a lot by being able to model galaxies in different ways. But also, astronomy is now a big data. There are surveys now of many millions of galaxies. We can look for correlations in those. And also within a single galaxy like our own, the Gaia European project, surveying stars, has observed 1.7 billion stars. So whereas in the old days, going back to Hubble on Mount Wilson, they just had a small amount of data. Now we have huge amounts of data, and luckily we have the computers to cope with it. So it's very exciting.
That's a very good point. All right, let's move on to chapter 3. Everybody knows that we need galaxies, that Dr. Dressler has given us in chapter 2, because that's the home of stars and habitable planets. But not everybody appreciates that we also needed galaxies to complete the other part of the evolutionary story that the Big Bang failed to do, namely to produce the heavy elements out of which we in our life are made of. And to give us that story in chapter 3, we have Professor Virginia Trimble from the Physics and Astronomy Department at the University of California, Irvine. She's an expert on white dwarfs, binary stars, supernovae, and also the history of astronomy. So Virginia, could you give us your perspective?
Morning, afternoon, or evening, depending on what time zone you're in. Let me start with a cliche, explain what it means, move on to the periodic table and some pictures, and then on to the present and the future. The cliche is that of the chemical elements, the early hot dense universe, the Big Bang that you just heard about, made hydrogen and helium. Burbage, Fowler, and Hoyle made all the rest. Now, who are Burbage, Fowler, and Hoyle? There they are, I think on Fowler's 60th birthday. If you can't see it, it doesn't matter. It's page 71 of your book. Now, you start with hydrogen and helium. You then work your way down the periodic table to the heavier elements, a few nuclear reactions at a time. What does a periodic table look like? It looks like that. It's color-coded. It's not correctly color-coded, but the main point is there are hydrogen and helium up the top all by their lonesomes, and all the heavier elements still to be made. And they're made in a series of nuclear reactions that start with a few light things that you've heard of, carbon, nitrogen, oxygen, on up to neon, magnesium, silicon, on up to iron, and there the star gets stuck. Iron is the most tightly bound nucleus. You can't do anything with it except let it collapse and make a supernova. But what does the Big Bang make? Hydrogen and helium, Burbage, Fowler, and Hoyle, meaning a 1957 paper where they traced out nearly all of the nuclear reactions that you need. Forward to 1974, there was a conference in Cambridge. Sir Martin was on he was only Professor Rees in those days. He was on the SOC. And this is a 100-page write-up of that conference. Yeah, I wrote it, so it must be right. But thank you. In the interval, what's happened? 1974 to the 1995 meeting, and on to the present and the future. What has happened is more. You've heard this already. Let me say it again. More data, more telescopes, more people, which means more competition, I'm afraid, and different kinds of people. There was a time when papers only had 2 or 3 authors, and it was so rare to have 3, we remember them. Egan, Linden, Bell, and Sandage on how to make galaxies. Hummus and Mayall Sandage on the distant scale of the universe. And still there were people quite often doing important things alone. The other picture on this page is Beatrice M. Tinsley, the first to do a quantitative study of how galaxies evolve. She died tragically at the age of 40. To us on the panel, this is incredible done.
Thank you. Thank you.
I'm afraid that I don't know who's listening. I hope there's somebody listening to whom 40 already sounds really, really old, because you are the future. Caitlin, if you're here, hi. You are the future. I have worked with a student 55 years younger than I am. I have some warnings and some advice out of this. The warning is that the latest idea or the latest data may not be the whole story. You've heard about the microwave background. It took a while to establish that was even from the early universe and not from sources. The X-ray background There were 10 different explanations. If they'd all been true, we'd been fried by X-rays. Getting across the periodic table beyond iron required multiple processes, some in stars like the sun and some in supernovae, some other places. But if every way people have suggested made our process, we'd be up to our Tritius and gadolinium. Professor Zuckerman said I could use that word. How old am I? Well, okay. The Large Synoptic Survey Telescope is now Vera Rubin. We all knew and loved Vera Rubin. W. First is now the Nancy Grace Roman Telescope. Not only did I know Nancy Grace Roman, I knew her mother. Advice, if you're given a choice of two tasks, take the one you don't already know how to do. And second, pay attention, because someday you'll be the only one who remembers. I've got to say something about the Nobel Prize. You know, announced like a week ago. And two of the winners are our own UC people, more or less. Andrea Getz, who's used the Keck telescopes, who's at UCLA. And Reinhard Genzel, who's used, among other things, mostly, in fact, the large, it's called the Very Large Telescope of the European Southern Observatory, but has Berkeley connections. And what's, I think, interesting in this, they've used stars at the center of the galaxy as probes of the black hole. But also those stars are different from the local stars. They form by different mechanisms out of different kinds of gas, more dense gas, among other things. And they will put out a different mix of elements. That is something still to be studied with more telescopes, more people, more data. Thank you very much.
Do you have any thoughts on that, Martin?
Well, just a bit of advice, as Virginia gave, for the young people watching, which is pick a subject where things are happening fast, where there are new instruments, better computers, more data, because then you won't be just filling in the details or doing the things the old guys got stuck on. You could do something new. So I think with the new telescopes coming online, there will be a chance to sort out the heavy elements. And of course, the idea that coalescing neutron stars can make some of them, which dates back to 1970s, is now being tested by events discovered by gravitational radiation. So it's an exciting subject to actually understand the origin of the very heavy elements and decide which among these many different ideas is the correct one.
You promised to mention Cameron if I didn't.
Right, yes. Let me say that B squared FH, the four people who wrote the classic paper, were in a sense duplicated by one man, A.G.W. Cameron, who was a polymath, and he was based in New York, and he wrote this in a government report, which didn't get such wide circulation, but he deserves to share the credit with B squared FH for what is really an amazing discovery, to discover that we are literally linked to the stars in a more intimate way. We each of us contain atoms from hundreds of different stars which lived and died before the solar system formed. So let's give Cameron his credit as well.
Thank you.
Thank you, Martin. One quick reminder announcement. We do want to have all of your questions to the panel, and you must use your chat window. Please open your chat window and then use the blue pull-down menu to find Ben Zuckerman, and that's the name of the co-host that you need to privately send your questions to. They have to go through Ben Zuckerman, and then he will feed your questions to the panelists for their responses. So please do that. Now, we've got a lot of bangs in this subject, and the next author of chapter 4, Alex Filippenko. Does he really need an introduction? Well, he, if you don't know, is a professor of astronomy at the University of California at Berkeley, and he is one of the world's leading experts on supernovae and the accelerating universe, things that go bang. Alex is all over it. Let's hear Alex's thoughts about what the progress in chapter 4.
Well, thanks very much, Matt, for that kind introduction. My chapter 4, has seen enormous modifications since 1995. A few of them have been mentioned already. Professor Ned Wright mentioned the discovery of the accelerating expansion of the universe, made initially with studies of very distant supernovae, showing that they're fainter than they were expected to be, and thus had been pushed farther out than would have been the case in a universe whose expansion is slowing down with time. And I was actually privileged to be part of that discovery. And now it's described in the revised version of my chapter. The next thing has already also been mentioned by Virginia Trimble, the supermassive black hole in the Milky Way galaxy, the discovery of which was officially recognized just a week ago with the 2020 Nobel Prize in Physics. Professor Andrea Ghez at UCLA and her team using the Keck telescopes, and Professor Reinhard Genzel of the Max Planck Institute in Germany and also of UC Berkeley using the Very Large Telescope in Chile. A magnificent discovery with which now and in the future, they'll be able to test certain strong field predictions of general relativity, what might be going on in detail in the immediate vicinity of a supermassive black hole. So that's a magnificent discovery. And although, of course, I wasn't able to discuss the Nobel in the book because it was just announced a week or so ago, I did talk about the supermassive black hole in the galaxy. Along those same lines of supermassive black holes, there's the stunning Event Horizon Telescope image of the glowing disk of gas around the truly giant 6 billion solar mass black hole in the galaxy M87, 55 million light years away. It was on the cover above the fold of hundreds and hundreds of newspapers in April of 2019, and we were able to sneak that image and a discussion of it into my chapter prior to going to press. Beautiful, beautiful image that really captured the imagination of much of the world, showing really the shadow, the silhouette of a supermassive black hole, and confirming the mass that had been determined through measures of aggregate stellar motions in the center of that galaxy. The next great discovery, recognized with the 2017 Nobel Prize in Physics, gravitational waves. First, from colliding black holes, having roughly 30 to 40 times the mass of the sun, greater than had been anticipated, and dozens of those have been found since then. And then the discovery of gravitational waves from colliding neutron stars. Moreover, an optical and infrared and radio and other electromagnetic wave counterpart of that neutron star colliding system. Wonderful, because this is really multi-messenger astronomy. We could look at that glowing counterpart and see through its spectrum the signature of the heavy chemical elements that Professor Trimble was talking about, particularly those that come from a rapid neutron capture process. Gold, platinum, silver, and the lesser known lanthanides and actinides come predominantly, we think now, from these colliding neutron star systems, and we've now seen evidence of that. And finally, the whole subject of gamma ray bursts, these tremendous flashes of gamma rays, high energy radiation that appear roughly once a day somewhere in the sky. Those were known at the time that the first edition of the book was written, but we didn't really know what they're caused by. We now know that those that last longer than 2 seconds, the so-called long duration gamma ray bursts, are caused by a special type of very massive collapsing star, which also produces a supernova. But there's a beam of radiation that in some cases can point our way, producing a tremendously bright flash. And then there are the short duration gamma ray bursts, which in fact are the colliding neutron stars. And in some cases, though we have not yet shown this, collisions between black holes and neutron stars. So those are the 5 topics I would say have seen the greatest growth since the first edition of the book. They're all covered in my chapter. I see the future as being bright. There will be surely an Event Horizon Telescope image of the supermassive black hole in the middle of our Milky Way galaxy. That's coming up. There will be more gravitational waves detected, hopefully one from a colliding neutron star and black hole. The LIGO-Virgo collaboration should start up with observations again in 2022 or 2023, depending on delays related to COVID-19. More optical counterparts will be found. That'll be fantastic. The nature of dark energy will continue to be studied. I'm not sure it'll be solved in the next 5 or 10 years, but we will continue to study it. And then, of course, as I mentioned, probing general relativity in the vicinity of the supermassive black hole in the Milky Way galaxy will be an active area of research. So this is going to be an amazing next 5 to 10 years. Thanks, Matt.
Thank you very much, Alex. Martin.
Yes. Well, huge amounts happened in this subject, and I really think that Alex should have written a much longer chapter to cover all these things in the last 5 or 10 years. A hell of a lot has happened. I'd like to say 2 things about Nobel Prizes. The first thing is that Alex should have got one, because the prize for the accelerated universe should have gone to the whole teams. It was really a misleading impression of how science is done to give it to just 3 people when there were several equally distinguished people who didn't get their share. So I think we should criticize the Nobel people for not recognizing group activity fairly. And this time, I think they quite rightly recognized Gensel and Gase, but I think it was slightly misleading to imply, as the press coverage did, but they didn't in their citation, that this was good evidence for an actual Einsteinian black hole, because none of these stars get close enough to actually tell us that the black hole obeys Einstein's equations. We had already much better evidence for the compactness from the compact radio source and variability. So I think it's slightly misleading to say that they discovered a black hole. They found better evidence for compactness, but we knew about that compactness already from other techniques.
Yeah.
So I was
I agree.
people, but congratulations to all that Alex has done and all the things he described.
Thank you very much, Martin. By the way, I agree with you entirely about the Nobel Prize, and would just add that really, if you look at the contributors, for example, to the incredible discovery of the primordial fluctuations of matter by the cosmic microwave background telescopes, we at UCLA strongly know that Professor Wright should have been included in that Nobel Prize. Not that we are at all obsessed about Nobel Prizes. It's just a landmark to remind us of our progress. Now, speaking of progress, so we've got stars being born, and now in chapter 5, our distinguished author Fred Adams, who is professor of physics at the University of Michigan, carries on the story. He's an expert on the birth of stars and the byproduct of this birth of stars, the disks of material that naturally form around them, where you can find planets being born. So, Fred, tell us your thoughts about that area.
Thank you, Matt. So this next chapter talks about the formation of stars and planets. You often think of stars as being permanent, or at least the ancients used to, but as we've already anticipated from the previous speakers, stars actually go through lifestyles. They're born, they live for a while by doing nuclear processing, and they often die in dramatic fashion, but one way or another, they end with a death-like closure. So at the time of the first edition, we had put together a working paradigm of star formation. And the basic idea is that we can see stars forming today, and they form in these great big clouds out in space. These clouds contain perhaps millions of times the mass of the sun. The star formation process itself actually takes place in small central condensations, so much smaller, denser regions within these clouds. These condensations collapse from inside out, and then a star forms at the very center of the collapse flow. A circumstellar disk collects around it, and that entire entity is surrounded by an infalling rain of gas and dust that falls on it. Eventually, an outflow develops, and then sometime later, the star disk system separates itself from its parental cloud, and we have a young star and eventually a planetary system. And then finally, after all of that, the star turns on and begins its nuclear processing. So at the time of the first edition, we had this paradigm in place, and I'm going to focus on just 2 things in the 2 minutes that I have left. Namely, one of the things that's critical to this process is the circumstellar disks. The natural size scale that the star formation process produces is not a stellar size in terms of a length scale, but rather a solar system size. And what that means is that all of the stuff from the cloud falls into a solar system sized volume. Now that structure contains a star in the middle and a disk around it, and most of the material that falls onto the disk makes its way onto the star through some kind of disk process. In the end, or in the beginning rather, we were only able to ascertain disk properties indirectly because our telescope beams were too large. We did not have the resolution to actually take a picture of the disk and see what was happening inside it. So one of the key things that's happened in the last 20 years is that telescope technology has developed to the point where we can now actually see inside the disks and see what's going on. And that sets the initial conditions for planet formation. And that leads us to the second big revolution that's happened in the last, the discovery of planets. So the first planet, the planet 51 Pegasi, which is a Jovian planet in a 4-day orbit around its star, was discovered just after the original symposium. This discovery was so large that it led to the recipient of yet another Nobel Prize. Last year's Nobel Prize was received by Michel Mayor and Didier Queloz for this discovery. Now, since 1995, we discovered the first multi-planet system in 1998, then the first transiting planet, the first planet that could actually be imaged, the first planet around a binary, the first planet as small as Earth, and then really an important shot heard around the world happened in 2014, when for the first time we were able to see a planet with the mass as small as Earth and at the location so that it's the right distance from the star that it could have liquid water. And since then, we've found thousands and thousands and thousands of other planets. So the next big thing, of which there are many, but the one I want to highlight is this. At the present time, we know a lot about the planets and the solar system orbits or solar system architectures, including their orbits. And what we like to know is the actual planet properties. So one way to do that is to look for the light shining through the atmosphere of a planet. And with present day technology, we can look at the atmospheres of big planets that are close to their stars, and we can ascertain some of their properties. This technology is now very primitive, but we already know that these big planets have water in their atmospheres. So the next thing, the thing that I think everybody's really excited about, is that over the coming decade or so, we will be able to measure the atmospheric properties, or we hope to measure the atmospheric properties of planets as small as Earth at distances as far as Earth from their stars, so that we can actually start to do these kinds of experiments on habitable planets. And of course, that's the next holy grail, is to really establish whether or not there are such habitable planets. Thank you.
Thank you very much, Fred. Martin, do you have any thoughts?
Well, this is an archetype, fast-moving, exciting subject where so much is happening. And of course, the next generation of telescopes, I mean, the James Webb, but probably even more the European ELT, the extremely large telescope. They're not very imaginative in their nomenclature in Europe. It's going to have a 39-meter mirror, 800 pieces of glass in a mosaic, and that will be able to separate out the spectrum of an Earth-like planet orbiting a star from the much stronger signal from the star itself, and do the kind of things that Fred mentioned, and perhaps find evidence for a biosphere, the so-called the red edge from chlorophyll, and evidence for ozone and things like that. So that'll be a really, really exciting subject. And looking even further ahead, you might expect to have telescopes in space which could actually resolve the images of some of these objects. And I mentioned in one of my books that a challenge would be to have a big space telescope which by 2068 can get an image of an Earth-like planet orbiting another star. I say 2068 because that's the centenary of the famous Earthrise picture from 1968, which had such a big influence on environment. So to get a picture of a planet like the Earth orbiting another star, that should be a challenge for those who are starting in astronomy today.
Thank you, Martin. Well, nobody here, well, hopefully some of you will be here to check on Martin's prediction there. Now, our chapter 6 author, Christopher McKay, dropped off the call, but are you back on? So I think he's trying.
Matt, if Chris is not on, he sent me an email warning me this might happen with his lousy home connection. So I could make a few remarks on behalf of Chris. It'd be very brief, though.
Right, we'll have him dial in. He can use the telephone. But yes, please do, Ben. That would be good.
Okay, so is Chris going to try and dial in? Yeah. Okay.
Let's move on. Okay, so yeah, go ahead.
Okay. Well, the one thing, of course, that when we're discussing.
Oops.
We lost it. Go tell him.
The universe are exoplanets, which been mentioned by a number of the previous speakers. So I won't say anything more about them, and except that again, the main question is to find one that's or some that are habitable, potentially habitable, and then see whether they actually are habitable. Another point that Chris thought was very important was the discovery of oceans in our own solar system, the outer solar system, especially on Enceladus. And there's actually this is one of the satellites of I guess Saturn, and this and Chris points to figure 6.6 in the book in this regard, and then there is the detection of organics on the surface of Mars by Curiosity rover. So there's possibility that there's might be some evidence for life, or at least what's needed for life and objects in our own solar system. There's actually been some press recently about discoveries in the atmosphere of Venus, phosphine, and some other molecules. In fact, glycine just came up on the preprint astronomy preprint servers. Glycine detected in the atmosphere of Venus, glycine being the simplest amino acid that's relevant for life on Earth. So there are quite a few exciting discoveries related to our own solar system and which of course we can study in much more detail than we can hope to study the prospects for life on planets or moons orbiting around other stars.
Matt, can I interject something?
Please.
We've said more telescopes, more data, more people, but different kinds of people, frankly. Egan Lindendale and Sandage would not get jobs today. I'm sure I would not, Fritz Zwicky would not. People have to be able to work in large groups, collaboratively, sharing what they're doing with a fairly rigid command structure. But the result is the paper that announced that neutron star merger had 2,000 authors. The first 3 are named Abbott. That paper is Abbott et al. I couldn't work that way. I don't think, Dr. Filipenko, I'm sure could, maybe some of the rest of you, but we're going to need different kinds of people as well as more.
Very good point. Martin, do you have any thoughts about the search for habitable exoplanets that is covered in Chris McKay's chapter 6 that Ben must have
well, I just make the point from what Ben said about looking under the ice of Enceladus, etc., that if we could show that life had originated independently somewhere else in our solar system, that would immediately say that there was life in billions of places in our galaxy. Because when we only have one unique origin we know about, namely here on Earth, we can't rule out it being a rare fluke. But if it happened twice within one planetary system, then that would tell us pretty convincingly that it would be widespread everywhere. So that's why it's worth looking in these places, Europa, Enceladus, and everywhere else.
Yeah, it's a very good point, and people are working hard on it. Well, so now we have even the most fun part. We get to have the panelists and moderator respond to the questions that hopefully have been submitted by people participating in the audience. And remember, you need to use the chat function and pull down Ben Zuckerman's name to send a private message to him. And so I think it's time to pretty much turn it over to Ben Zuckerman to pick the questions and in an appropriate sequence, I suppose, and feed them to our panelists and see what they have to say.
Okay, thank you, Matt. Well, we have a number of quite interesting questions. I'll start with this one, which is meant to specifically for Alex, but I guess anybody can chime in if they would like. Alex, you stated in chapter 4 of the book that smaller black holes can evaporate. What happens to the matter when a small black hole evaporates? And what is the mechanism that drives this evaporation?
Right. Let's see, am I unmuted and
Yeah, yes.
Okay,
Speak
great.
up.
Yep. So that's a great question. It's thought that black holes can evaporate through the Hawking radiation. So this is the theoretical discovery for which Hawking is probably most famous. The idea is that, well, you can think of this several ways, but for example, a particle-antiparticle pair can form just outside the boundary, the event horizon of a black hole. And in some cases, one of the particles, doesn't matter whether it's the particle or antiparticle, it goes into the black hole. And as seen from the outside, it goes in with negative energy. This is a purely relativistic effect. I don't have an analogy for you, but that allows the other particle to escape to infinity with positive energy. And so this leads to a slight decrease in the mass of the black hole. You can also think of it as particles tunneling out of a black hole through a quantum mechanical process, a little bit like radioactive decay is a tunneling process. So this is incredibly slow for supermassive black holes or even stellar mass black holes. But for little tiny black holes that may have formed as a result of density fluctuations shortly after the Big Bang, the process is non-negligible. And the ones that are less massive than roughly Mount Everest will have already evaporated with an explosive flash at the end of their lives. And those that are more massive than about Mount Everest are still on their way down. The process accelerates as the mass gets smaller and smaller. And at roughly 10 to the 15 grams or so, Mount Everest or so, those are the ones that should be going off right now. It's a beautiful idea. It's the first steps in unifying the two great pillars of modern physics, quantum physics on the one hand, the physics of the very small, and general relativity, the physics of the very large on the other hand. We think that any generic theory of quantum gravity will have this property. It's not specific to any particular process. The problem is that these explosions of tiny black holes going off have not been detected, which either means that, you know, the theory is wrong, but more likely these little tiny black holes don't exist in sufficient numbers for us to have likely seen one while we've been watching the sky. At least that's what I like to think, because I hope that the Hawking mechanism is correct. But that's the basic idea.
Bekenstein.
Well, Bekenstein showed that they have an entropy and they should glow, but he stopped right there. He didn't take that next leap to say that a black hole is a black body and thus really does radiate, Virginia. But I agree, Bekenstein made great leaps. He just didn't make that final leap the way Hawking did.
Thank you, Alex. Let's see, here's another question from our audience. Several decades ago, topological defects arising from guts, such as cosmic strings, domain walls, and magnetic monopoles, were discussed extensively. Where does the community stand today on the cosmological relevance of such theoretical constructs? Ned, you might try that one, or anybody. Martin, Ned?
Yeah, well, I certainly would want to say something about that. So one of the predictions of cosmological defects or cosmic strings, which actually would produce line-like features, linear features across the cosmic microwave background map. And as we have gone to higher and higher resolution maps with WMAP and Planck, we have not seen any of these line-like features, you know, little scarfs across the map. We don't see them. And so evidently they're not very significant. So they were a possibility, but further observations have shown that, well, they might be around. It's just like the small black holes. They're not around enough to be a significant factor in the cosmology.
And inflation, the way the monopole.
Well, let me add something to that. In addition to the lack of a signature in the cosmic microwave background, the statistics of the density fluctuations that you get from cosmic strings are different than the statistics that you ultimately see in the microwave background maps that Ned and others have put together. Now, the particle theorists, never to be idle, have come up with a new kind of cosmic string where the old cosmic strings that we're talking about here were invented or thought to be part of the galaxy formation process, and that is sort of safely ruled out. But the particle theorists now do talk about a new kind of cosmic string that has less mass so that it can get around all of these observational bounds, but it still does some of the interesting things from a particle physics point of view that they originally invented them for. And you should also perhaps mention that there's direct detection experiments for magnetic monopoles that have also come up empty, so that we have much stronger limits on the monopoles. And as far as we know, we haven't seen any.
Or just one.
Or yeah, just one in Stanford and
But
perhaps you should tell that story, Ed.
you only need one to quantize charge.
Okay.
One in the whole
Any-
universe.
Okay, anyone else before we go on to the next question? Okay, that was very, very interesting answers there, I think. Okay, so Roger Penrose just shared the the 2020 Nobel Prize in Physics. So one of our audience is wondering whether or not anyone would like to discuss Penrose's conformal cyclic cosmology, which makes the question of the origin of the universe moot.
Is no a possible answer? I mean, he's a wonderful guy. I never understand anything he says.
Well, apparently the Nobel Committee did, Virginia.
Well, can I say
Yeah.
something?
Go ahead, Martin, please
Yeah,
do.
okay. Well, his theory, it doesn't have much traction with other theories, but it's rather neat because his point is that if you imagine the far future of the universe, of the kind that Alex discussed, it gets emptier and emptier, and eventually there's nothing in it apart from photons, perhaps. And photons go at the speed of light, so no time passes if you're a photon, because the time dilation is infinite. And so, in a sense, there's no scaling. And so his idea is that you have this empty universe, and then you rescale, and you start again from that. So it's a nice written idea. But going back to Penrose's life's work, he's been working for more than 60 years. He's amazingly imaginative. But I think what was highlighted by the Nobel people was that he was really the instigator of the whole body of work, which involved Hawking, Israel, and many other people, which led to the realization that singularities and black holes really existed, and led to us delineating the properties of black holes. So he was really the great pioneer. And I think most people would say that the two greatest figures who have done more than anyone else since Einstein to enhance our understanding of gravity were Penrose and Hawking. And it's really rather sad that they didn't give this prize a few years ago, when it could have gone to Penrose and Hawking jointly.
Yes.
Yeah, right. Well, it's too
Yeah,
late
so
for
I'd just
Hawking.
like to, add one thing. So there was some predictions. Penrose's cosmos producing special circles on the sky, but the statistics weren't actually verified. So it turns out that there's a lot of weird things on the sky, and so there's no statistical evidence for his cosmology in the CMB sky.
But Hawking's initials appear.
Yeah, but Hawking's initials appear, definitely. So lots of weird things show up when you had a random map.
Okay, Ben?
Any other comments? Okay, let's see. Here's a quick one for Virginia. one of our the audience would like to know the reference information for the paper on the origin of the elements that you referred to. Is this in Reviews of Modern Physics, Virginia?
Reviews of Modern Physics, 1975, and the volume number is 47. It starts on page 877 and goes on for 100 pages. And it arose out of that meeting, and I was taking notes, and a colleague who was quite limited in her English said, could she have a copy of my notes? Well, nobody can read my handwriting, not even me. So I had to type them all up. By the time I typed up 2 weeks of notes, I was well on the way to a review paper. And Ed Salpeter, another wonderful person, who was the first to sell to the community that you bring 3 heliums together to make carbon fusion, helium fusion, said, he was then one of the editors. He said, well, write it up and send it to Reviews of Modern Physics. So I did.
And I just want to point out all these important references are in each chapter, laboriously compiled. This has got a lot of material in it.
Let's see. So here's a question from a social scientist who says, Matthew Malkin and Benjamin Zuckerman conclude the preface with a reflection on what human intelligence needs to be. How can those of us in the social sciences draw on the work of astronomers to think about problems facing humanity? And then I guess there's a quote from our preface and about human beings we're going to have to act smarter if we want to take care of, are we truly intelligent or only technological? And our intelligence should be much more than it's been shown to be so far. So anyway, that's one comment that maybe.
We need different kinds of people. I don't know how you arrange that.
Well, maybe we're going to all be made out of, maybe our descendants will be mostly made out of silicon, and that us carbon-based creatures won't be very important in the distant future.
Will the silicon-based creatures be better at collaboration?
Well, they'll have Bluetooth.
Oh, that was a question to Martin, I think. Will the silicon-based creatures be better at collaborations?
Yes.
Here's another life-based life. Sorry, Martin, go ahead. What?
I was going to say, but seriously, they might be less aggressive because Darwinian evolution favors intelligence, but also aggression. Whereas what you might call secular intelligent design, whereby machines design better ones and go in that way, this might favor intelligence, but it needn't require aggression. So that's the good news, Virginia.
Thank you. We need some.
Well, that may be related to another question. Is evolution an appropriate word for the contents of the universe? Galaxy and stars do not inherit features from survivors in earlier generations. If our descendants are able to construct creatures very different than ourselves, computers or artificial intelligence, whatever you want to call it, that's very different than our carbon-based creatures. Is that evolution, or is it something else?
Could I say, I think it's a great pity that astronomers use the term evolution at all because of the confusion the question is raising. Development would be far better. We talk about an embryo developing and turning into an animal or something like that. And so if you talk about the development of galaxies, development of stars, that I think would be less confusing.
But they do inherit the chemical composition from previous generations.
Right, but not the morphology. Yeah. Mm-hmm.
Well, the confusion is that the stars have a lifetime or a development time, and we call that evolution. But then in addition, from one generation of stars to the next generation inherits the heavy elements that Virginia talked about. Right. That's more like evolution, but still not quite biological evolution. Right. So we're very confused in our nomenclature.
Yes.
So our apologies.
Also for population 1 and population 2.
Yes.
Now here's an interesting question. could the panelists comment on the Hubble constant tension, the current disagreement between the CMB concordance model value and direct measurements via distance indicators? Whoever takes this question up, please sort of give a few words of background as to what the problem, what the tension is.
Yeah, I could comment on this, and probably Ned Wright would want to comment as well. Let's see, I guess I'm on now. So I'm involved with the team, again with Adam Rees, in measuring the actual value of the expansion rate of the universe at the present time. That's the so-called Hubble's constant, where you have the speed of a galaxy as Hubble constant times the distance, all right? And we've been making these measurements by looking at supernovae in nearby galaxies and also measuring the distances of those galaxies using the tried and true method of Cepheid variable stars. So we get an answer of roughly 74 in some units, kilometers per second per million parsecs, but whatever, 74, plus or minus about 1.5. There's another way to make a measurement of the constant, and Ned Wright can explain this in greater detail. But the idea is you make measurements of the early universe, the cosmic microwave background radiation, and then using the standard cosmological model where you've got a universe filled with dark energy, dark matter, and normal matter. You evolve that over 13.7 billion years, and you then predict what the current rate should be. And they get a number of order 68 plus or minus 1. Now, these numbers differ by about 5 standard deviations at this point, which is considered a discovery, at least in particle physics. There's only about 1 chance in 2 million that it's the statistical fluctuation of no physical significance, as long as we've all taken into account possible systematic errors. And there are other methods now besides the supernovae of measuring the local current expansion rate, and they seem to agree with what we came up with supernovae. So it's a real tension. It may indicate that there's something new in the universe that we have not yet taken into account in evolving or predicting from the cosmic microwave background measurements what the current rate should be. And I think it's a very, very interesting problem.
When do we get a LIGO number?
It'll take a while.
The big error bars.
Yeah,
The error bars are very big for LIGO.
But that is smaller. When will it be useful?
You need 100 standard sirens for them to be competitive. And so far we only have 1.
Look, there was once a first gamma ray burst too, and a first Cepheid. And a first
so maybe
galaxy.
Ned wants to comment whether he thinks there's a significant tension there, or there's something wrong with either the near field or the early universe measurements or extrapolations or whatever.
Well, I would like to say that it's probably something systematic, but also being older than Alex, I remember when it was H naught is 50, no, H naught is 100, and people would almost get into fistfights over that. And now we're arguing between 74 and 68. So there's been a strong convergence, and we're fighting over the, down at the county level now, but, the global parameters of, how the universe got started are, much better established now. And while it's worthwhile working on these measurements, it's, to my mind, just remarkable how much things have converged.
Well, they have converged, but the really exciting thing about this is that it offers the possibility of a whole new revolution. If this discrepancy is real and not caused by some error or some systematic effect, then it means that we've left something out of our cosmic picture, right? Of our cosmological model. And one idea is that there's a fourth light sterile type of neutrino, and that would change the extrapolation from the early universe to now. Or maybe dark matter interacts with light in some weird way, or maybe there's something else. Maybe there's some curvature to the universe. There's a number of possible explanations. And so it's often in these details. I'm not arguing against the convergence, I agree with you, but it's often in these little details and these, at least initially seemingly insignificant differences, that you actually get something really new and exciting.
The orbit of Mercury and general relativity.
Yeah, or the decay of the binary pulsar, the Hulson-Taylor, evidence for gravitational waves. It's only by measuring the pulsar periods to n significant digits that you could possibly hope to get this result. So science and astrophysics in particular are replete with examples of this sort. So I would take it seriously, Ned.
Physics.
Okay.
Everybody wants it. Almost everybody.
Okay. Thanks, Alex and Ned. Let's see. I guess we have time for maybe two more questions. One is, I guess Ned would be the most relevant person for this one. Ned, you mentioned the role of sound waves in forming structures in the early universe. What about alphane and magnetosonic waves? When did they get started, and did they play a role in structure formation?
Well, as far as we know, not. I mean, there's very strong limits on the intergalactic magnetic fields, and they are produced. Magnetic fields are produced when you have conducting material whirling around in a suitably complex pattern, whether it's in the sun with the convection currents in the sun, or in the earth, or in an electrical generator. And so once you have enough sort of circulating motion, but it can't be too simple, any symmetric pattern of currents actually doesn't produce a self-regenerating dynamo. But once you get into a complex pattern, you generate magnetic fields. So they grow very strongly once you have shearing flows and electrically conductive matter. But we didn't apparently have much of that going on in the early universe. So it would appear that the magnetic fields are pretty much shorted out by the fact that we have good conduction and not a lot of shearing motions. So that would be the standard model. It's sound waves and not alphane waves.
Okay, thank you, Ned. Let's see, I said that will there be just one more question after the one that Ned just responded to, but maybe we have time for two. Let me just tell you what the two remaining questions are, and then we'll see how that goes. One is the question of, would anyone like to take a guess on, make a guess about the number of Earth-like planets in the Milky Way galaxy? And the other question is related to the groups. The fact Virginia mentioned that so many more authors are on a typical paper in the Astrophysical Journal now than when Virginia and I were starting in astronomy. And so the question from two people actually, do great ideas come from groups? And does anybody believe that? And one comment along with this question is, collaboration is needed to confirm the details of great ideas, but do groups originate these ideas? So those are sort of the last questions about number of Earth-like planets in the Milky Way, and about whether original ideas come from groups.
Well, let me say something about the Earth-like planets, and then I'll let the discussion, and I'll be quick, and then the discussion can address the second question. The astronomers have worked very hard to estimate what's called eta Earth, which is the fraction of solar systems that have what they call an Earth-like planet. And depending on how you do the systematics and call your error bars, the number is anywhere from 1/10 to 3/10. So we think about 1/4 of the stars have what astronomers call an Earth-like planet. Now, to be clear, these Earth-like planets are planets with masses within a factor of 2 of Earth mass and with a surface temperature, estimated surface temperature that has the right range to allow for liquid water on the surface. So the number of potentially habitable planets is enormous. You know, each solar system has a good chance of having one. The problem is that beyond that, you want your planet to actually be habitable, to actually have water, not only that it could have water. And there we just don't know, we have no data. So the first part of the question we know really well, I would say, especially compared to 20 years ago. And the second part, we're still waiting. So that's sort of where we are. And I would move on to the second question.
Great ideas come from interactions sometimes. Yes, they come from individuals, but sometimes they come from 2 or 3, maybe not a whole committee, but 2 or 3 people bouncing off each other. The Hubble Fellowships, one of the great ideas of sociology 30 years ago, was something that Chris McKee said to Ricardo Giccone a long time ago. And it was a fertilization of an interaction of 2 people that gave rise to that great idea.
Anyone else want to comment on groups, ideas, anything? If not,
Well,
I guess we're about at the end.
It was a little before my time, but I think from reading the history, when the Manhattan Project was going on, the physicists were very adamant that they wanted to have groups and group interaction. The military wanted to sort of compartmentalize everybody and not let anybody talk to each other. And the physicists argued that we should, or they should be able to talk to each other in order to develop ideas and cross-pollinate and actually make progress. And I think in that particular experiment, the physicists won out and they were able to develop what they needed to develop. We could argue after the fact whether that was a good thing or a bad thing, but in terms of getting something done, it was very successful.
I'd like to make a comment about this. One thing that might be raised by this question is, does it take a group of 1,000 people or even 100 people to come up with a good idea? And I think the answer to that is certainly no. It doesn't mean that groups that are large, that are doing projects that require large groups because of the resources and the kinds of work that has to be done, it's just way more than small numbers of people can do. It doesn't mean that those groups don't need to be that big, but it might mean that the new ideas and the novel things that the group does read down to a few people, like Virginia was saying. So it's not, you just don't talk about it in terms of that group of 100 or even 1,000 people came up with a great new idea. That is probably not very common. But in fact, the more interesting question then is a big group structure that we have now more conducive to generating new ideas from small numbers of people? Because if it's going to work better in that environment, that's good. If it works worse, then that's a bad byproduct of the way we do science now.
Well, you know where the first ever idea that you might look for gravitational waves came from. It was one person. He died almost exactly 20 years ago. But
You know what I believe about this?
I'm sorry, but I really
even think of looking.
I was really expecting, all right, let's hear from Martin. I really want some more people to tell me how many Earth 2s you think are out there in our galaxy. Let's hear from Martin.
Yeah, well, no better answer than what Fred's given. But on the other question, I think what is wrong is the fetishizing of a scientific paper, which is obviously a paper with 1,500 authors. Is a bit ridiculous in a way, although you need a big team. So I think what we want to do is to give people more credit for blogs and informal interactions and all that, and get away from this system where universities only take notice of refereed papers. That's clearly not the right way to recognize the people on these multi-author works. So it's we've got to get away from the standard journals and realize that people contribute in lots of ways and give them credit for that. So the blame, I think, lies with the universities.
You're here.
Okay.
Okay, well, if we're done, I guess World staff person will take over and maybe close the meeting. Somebody there from World?
Hi, yes. Thank you, everybody, for such a great talk. There we go. So, as Nobel laureate Adam Rees puts it, this book is an exhilarating tour of the universe from true experts. For those who thirst to know how we know what we know about our place in the universe, reading this book will be a richly rewarding experience. And just to let you know, we are providing 30% discount to this book until Sunday next week with this discount code. And don't worry if you can't remember the code, as we will send it to you in a follow-up email. And we now have come to the end of today's webinar. It's been a pleasure having all of you, and we look forward to seeing you guys at future events. Please subscribe to our Facebook page and YouTube channel for more information and future updates. Thank you and goodbye.
Goodbye.